Okay, for your quiz today, hi Savannah, by the way.
Hi Savannah.
So this is your review, and then, yes, you have a quiz. So on your quiz, you need to be able to evaluate limits. So, for example, something like this. I'll write it down. Of course, I was going to do that anyway. Say this. Let's see here. The -4 is probably the problem, right? So 2. Let's see. Okay, and we'll do another limit. Let's say we have x approaches 2 square root 3x plus 5, and root more.
I'm going to turn my phone off.
Okay. All right. So for the first one, what do you think we should do?
Factor.
Yes. Why can't I just put this 4 in?
Because it'll be 0 and done it.
Yep. So we're going to factor. Alright, so we factored. Okay, so we can put in the 4. So we get 6 over 8, which reduces to 3/4. So apparently I don't know what just happened there. Is this still going? Now it's back. I don't know what happened. Alright, well, I guess we're back in business. Alright, so 6/8, we put in the 4, and we get 3/4. Alright, how about the next one? The one to the right. What do we do?
Don't you? You rational? Just substitute in, right?
Yep, just substitute it. So we get square root of 6 plus 5, which is root 11. There's nothing weird going on here, so that's our limit.
You usually don't ask us when there's nothing weird going on.
Okay, now for these two, we're going to use the function at the right, and notice it's a piece function, meaning that I have it divided into 2 pieces. And you could have more pieces, and this says to evaluate the limit as x approaches 4 from the negative side. So that means I'm going to be looking at this bottom piece because that's because it's defined as this for anything less than 4. So since we're coming in from the left-hand side by the negative, I'm going to use this piece right here. So that's going to be 2 times 4 minus 5, which is 8, minus 5, which is 3. This one is coming in from the right, so that means I'll use this one because it's defined as x plus 4 for anything where x is bigger than 4. So I get 4 plus 4, which is 8. We good? Any of this do you need to see again? Then we have infinite limits. So if I wanted to take the limit as x approaches infinity, oops, not 8, infinity, of say 5x squared minus 10x plus 4 all over 2x squared minus 3x minus 8. Really, it doesn't matter all this extra stuff. When we're talking about infinite limits, the highest power of x is what matters. So I can ignore all this extra stuff, and really I just need to be worried about the highest power of x. So when I just look at this, because all this is going to not matter, the x squareds would cancel, and that would leave me with 5 halves. So as x gets really, really big, this thing approaches 5 halves. We could have another case, say where I change that slightly. Again, same reasoning. The highest power of x is what's going to matter. So I don't need that extra stuff, I just look at this part. Okay, so it is important to write them in order. As x gets really, really big, we'll see one of the x's would cancel, so I'd have 5 over 2x. And you wouldn't even necessarily have to write that, but what you need to recognize is anytime I have a situation where I'm having a limit of a fraction like this, and x gets really, really big, that's going to approach 0. So this thing, even though there's a 5 over 2, since after canceling I'm left with x in the denominator, and x is getting extremely large, this is going to approach 0. If for some reason you forget how to do this, you could always choose a large value for x, say 100,000, put it in your calculator and just see what it appears to be approaching. That won't always work, but it is a trick that you could use. Let's flip this around. Okay, and then this time when I go to do the limit, I have 2x over 5. Again, same reasoning, the highest power of x is what matters. And now the x is in the numerator, it's going to get extremely large without bound, so that's going to approach infinity. And if I had a negative here, then it would be going to a negative infinity. All right. Any questions on infinite limits? We did infinite limits, I think, when we did horizontal asymptotes. Basically, horizontal asymptotes. Just stuff. Next thing would be find the equation of the tangent line. So in this case, we're going to be given a point, or at least an x value. So let's say f of x, which is another way of saying y. Let's say that equals x squared plus 2x minus 5. And I want the equation of the tangent line at x equals 2. So when I want the equation of the tangent line, I need to remember my point-slope form. There's my point-slope form. I need a point and a slope. Now I'm going to get the slope from the derivative. The point I'm going to get from the function. I would highly recommend you get that part first so you don't forget about it. And it's the easiest part to get. I take this 2 and I put it in for f. So f of 2 is going to be 2 squared plus 2 times 2 minus 5. Remember to put this in parentheses because if it were negative, that would make a difference. So we get 3. So that means I have y minus 3 equals m x minus 2. No squares or anything extra. Now I find my derivative. So I'm going to find f prime of x. To take the derivative, I use the definition of derivative, which is f of x plus h minus f of x, all over h. This is simply slope, which is why it's going to work. So I replace all instances of x with x plus h. So that's going to be x plus h squared plus 2 times x plus h minus 5. I'm going to erase this. It was 3 and 2, right? So I'll put that up here just so we don't lose it. We're going to fill that in. Minus, that minus has to distribute to everything. F of x, which is this x squared plus 2x minus 5. All over h. We distribute, we expand, so we get x squared plus 2xh plus h squared plus 2x plus 2h minus 5, distribute that negative, minus x squared minus 2x plus 5, all over h. Okay, hopefully you see how I expanded that. Make sure you do this expansion right. It's not just x squared plus h squared, is it? It's x plus h times x plus h. This piece right here is what I'm talking about. Then we do a bunch of canceling. The x squareds cancel. Those two x's cancel. The 5's cancel. Leaving me with 2xh plus h squared plus 2h all over h. And what I'm doing, oh, I forgot, we're taking the limit as h approaches 0, right? Limit as h approaches 0. Limit h approaches 0. Limit as h approaches 0. So now we factor out that h. So we have an h out here, 2x plus h plus 2 all over h. Limit as h approaches 0. Those h's cancel, and now I can evaluate my limit, and I get f prime of x equals 2x plus 2. Because that h goes to 0, right? I put in 0 to evaluate my derivative. Now, I want the value of the derivative at 2, specifically. So I do f prime of 2. So I put a 2 into here, and I get 4 plus 2, which is 6. So that's the slope of my tangent line. 6 goes there, and now I've answered the question. Are we good? Any questions on any of that?
Savannah has one.
Sorry, Savannah, I can't hear you. Because you're digital, that means you're not real.
Oh.
Yeah.
Alright, this would be just find the derivative. Let's say y equals 3 root 2x plus 4. Alright, so this would be the same as saying f of x equals 3x root 2x plus 4. We're going to use the definition of derivative, so limit as h approaches 0, f of x plus h minus f of x all over h. And then we put x plus h into this, so we get 3 times root 2 times x plus h plus 4 minus 3 times 2x plus 4, because that's my function. And we need to eliminate this h. There's no direct way to do that. I can't factor out h of anything. This is where I'm going to do rationalize. But instead of rationalizing the numerator, I'm going to rationalize the denominator. Instead of rationalizing the denominator, because there's nothing to rationalize down there, I rationalize the numerator. So I'm going to multiply by 3 root 2 times x plus h plus 4 plus, opposite in sign, 3 root 2x plus 4. All over, same thing.
How small can Cambridge?
Not too small, I'm limited by the computer. Alright, so now what's going to happen is I distribute this times that, and then this times that, and that. Now, I don't want to spend the time writing it all out. From your experience, if I had, say, root 2 plus root 3 over 4, and I was rationalizing that numerator, I would multiply by this. It's going to be the same idea. This times both of those is going to be root 4 plus root 6, because 2 times 3. Actually minus, because that's a minus. So minus root 6. And then the next one plus root 6. And then minus root 9 is in the numerator. I'm just doing the numerator. This is a 2. So notice the roots undo each other. Notice the middle stuff cancels itself out. That's always going to happen. So I don't need to worry about it. And then the last thing, root 9, so minus 3. So notice again, the roots undo each other. That happens every single time when we're rationalizing. So we don't need to do all this multiplication, because when we rationalize, the same thing happens every single time. Now, 3 times 3 is going to throw this off. 3 times 3 is 9, and then I have root. Well, I don't have a root because the root is undoing itself, times 2 quantity x plus h plus 4. Minus, okay, 3 times this, so 9, and then the roots undo each other, so 2x plus 4. At the bottom, I'm going to have an h. I'm not even going to multiply it out, because I want to cancel the h. So I'd be doing a lot of extra work for nothing. Okay, so that's what we get after we do all that multiplying. We can go ahead and distribute and everything. So this is going to be 2x plus 2h in there. So I'll distribute the 9. So I get 18x plus 18h plus 36. Distribute that 9, minus 19x minus 36, all over h times all that stuff. That 4 is inside of there. Okay, let's see what cancels. Those, and I have an 18h, right? Which means the h's cancel, don't they? So I have limit as h approaches 0 of just this 18's left. 18 over that h canceled. At this point, I can now evaluate by putting in h. H is 0, so that's going to go to 0. So I have 18 over 3 times root. That became a 0. 2x plus 4. There is no thing there, so plus 3 root 2x plus 4. Notice these are like terms. So, and I can cancel with the 18, so I get 6 over. Actually, I don't want to do that quite yet. 3 plus 3 is 6. These are like terms. 2x plus 4. Now I'll cancel that and get 18 over 3 root 2x plus 4. That is my derivative. That's f prime of x. Okay? That's about as hard as they get, so.
Do one without the root.
Okay, last example. Let's say I have 3x squared over x plus 2. And I want to find that derivative. I'm going to take the limit as h approaches 0 of f of x plus h minus f of x all over h. I replace x plus h into x, so I get 3 times x plus h squared minus 3x squared. I want to make sure that's in parentheses. This second thing, this minus f of x, make sure it's in parentheses so you correctly distribute that negative all over h. Oh, I forgot my denominator, didn't I? That would be x plus h plus 2. See, I replaced that into this. Don't forget your denominator. X plus 2. Okay, so I have a lot of problems here because of this h in my denominator. So our trick here, we don't have to do any weird rationalization or anything like that, but I do need to actually add these, which means I need a common denominator. And my common denominator is going to be limit as h approaches 0. My common denominator is x plus h plus 2 and x plus 2. So, common denominator, x plus h plus 2 times x plus 2. Because that's my common denominator for combining these fractions. This fraction is missing the x plus 2. So I have 3 times x plus h squared times x plus 2 minus this denominator is missing the x plus h plus 2. So I need to multiply by the x plus h plus 2. And then all over h. Now, boy, this is a really hard one. Now we need to actually expand. So I'm going to do my expansion up at the top right here. I'm going to do that x plus h squared. That's going to be x squared plus 2xh plus h squared. And then I have that. There's going to be a 3 out there and an x plus 2. I'm doing this piece up here. And then I need to multiply those out. So this times that, x cubed, this times that, plus 2x squared. Now this times that, plus 2x squared h. This times that, plus 4x h. This times that, plus xh squared. This times that, plus 2h squared. And then I multiply it all by 3. 3x cubed plus 6x squared plus 6x squared h plus 12xh plus 3xh squared plus 6h squared. Then I'm going to do this. I'll take the negative with it. So that's going to be, I'm doing this piece right here. So that's going to be minus 3x cubed minus 3x squared h minus 6x squared. So some things cancel. If I look at these, some things cancel. Those cancel. Those cancel. And everything that still has an h in it does not cancel. So that leaves me with limit as h approaches 0. So there's a lot of, you can do it, but there's a lot of little steps. What if we have a fractional thing here? We need to actually combine these fractions, which means we are going to have to expand those. We get our common denominator. Don't get lost in work. Do this little extra work off to the side and then come back to your derivative. Don't try to write it on this derivative. It's going to get really messy. So we were left with 6x squared h plus 12xh plus 3xh squared plus 6h squared all over this quantity. I don't need to expand that because of what we're about to do. We are going,
The minus 3x squared h.
did I miss one? This one?
The one.
This one?
Yeah.
Oh, did that cancel anything? No, it did not. So minus 3x squared h. Good catch, that would have thrown this up. Alright, so this is a big division problem. We keep, we flip, so times h, and we change to multiplication. So what happened? Oh wait, keep flip. I didn't flip it right. I'm like, wait a minute. This should be on bottom. I didn't actually flip it. Okay, so hopefully you see we can factor an h out, right? So that h cancels, one of these h's cancel, one of these h's cancel, and that h will cancel with that, because I factor it out. I'm just trying to save us a step. And then we have 6x squared plus 12x plus 3xh plus 6h minus 3x squared all over this stuff. And we take the limit as h approaches 0. Okay, so if we put in a 0 at our denominator, we get x squared plus 4x plus 4. In our numerator, we will get 6x squared plus, wait, those combine. How come I didn't combine them earlier? Aren't these like terms? Those are like terms. So those combine. So that's 3x squared. That will go away because we're going to 0, and then plus 12x. And that is f prime. Alright, that's all the time that we're going to spend on our review. Now, what we're going to try to do in the last minutes of class here is actually start what we should be doing today, which is rules of derivatives. Did you follow the process?
Yes, that's why I wanted to watch you do it before I wrote it down. So that
Okay.
I could, like, comprehend things. This was a lot to take in.
Now, what we are about to start today, you are not allowed to use on this quiz. Okay? You have to use the definition of derivative like we've just done on the quiz. It means a lot of expanding, a lot of this extra stuff.
I could not make them more terrible.
But the rules of derivatives, there are a lot of rules of derivatives, but the advantage of using the rules of derivatives is that you will not have to use this. This goes away. Which means you don't have to worry about canceling out h's or doing all this expanding. The rules of derivatives, if you buy into memorizing them, make your life way simpler. Alright, I'm going on, so you can copy that later. I'll have it saved. Rules of derivatives. We are not going to get them all today. So you couldn't even actually, for the most part, you couldn't even use all these rules yet because they'll be incomplete. The first rule that we'll do is going to be our, well, if I have something like this, if something like this is my function, then my derivative will always end up being n times a x to the n minus 1. Now that looks really nasty, but just watch for a second, please, because it is really, really easy. If I have this function, okay, to do this derivative, it'll be this exponent times this, 12, x, decrease the exponent by 1, plus, do the same thing here, this exponent times this, 4, decrease this exponent by 1. This exponent, we pretend it's x to the 0. 0 times 5 is 0, so it goes away. So that is the derivative. Done. Okay? Now, could you use that on something like this? Nope, because you have something way more complicated. You have a fraction here, so that would not work. But we do have a rule for that, but we probably won't get to it today. If we had something like this, f of x equals 4. I mean, and just kind of thinking, what is, this would be essentially a horizontal line, right? At y equals 4. And derivative is slope. What's the slope of that? 0. So the derivative of any constant is 0. Or also, you could think of it like that as the previous thing. F prime of x of, say, 7x squared plus 3x minus 10. Let's do that derivative. What do you get? What'd you get? Huh?
14x.
14x, then what? It's not just 14x. What's the exponent on this x right here?
1
A 1. So what's 1 times 3?
3.
So plus 3. And then I decrease that power by 1. Okay, so it's x to the 0 is a 1, so I don't need to worry about it. Okay? Okay, we could do something like that using the power rule. It doesn't look like we can, but we can. I have 2. If I rewrite this exponent, it's 1/2, so it's to the 1/2 power. So I use the same rule, this times that. That's 1. And then I decrease this by 1. So what's 1/2 minus 1? Well, that's 1/2 minus 2 over 2, which is -1/2. Now we need to agree, well, how are we going to write that? We'll go ahead and write that as 1 over. We move that down to our denominator, which makes it positive. So it's 1 over x to the 1/2, which equals root x. We won't bother rationalizing. We'll just leave it like that. So that's f prime of x. Okay? I'm going to put 3 examples. Well, let's do one more example of that. Let's say f of x is 5 root x. Let's say this f of x is 12x to the 4th minus 3x cubed plus 9x squared plus 4x minus 7. And we would all agree using the definition of derivative on this would be terrible. We would have to be putting in x plus h into these and expanding that to the 4th power, expanding it to the 3rd power, to the 2nd, and so on. That would take forever. So the rules of exponents, if you buy into them, make this way easier. And then I'm going to put this one up just because to fool you. So go ahead and do these first 2 and just think about that last one there for a moment. So remember, for radicals, change it to its exponential form. Then apply our rule. We good? The next one should be 48 x to the third minus 9x squared plus 18x plus 4, and then that goes away. All constants just turn to 0, and that's going to be f prime of x. Now the last one is a memorized one. The derivative of sine, this is a rule, is going to be cosine. That's a memorized. You just have to memorize that. The derivative of sine is cosine. The derivative of cosine is not sine. The derivative of cosine is negative sine. Okay. We're going to end class with the chain rule. We won't get too much into it, but before we even really dive into that, I want us to get used to this different notation. So let's say I'm taking the derivative of that. Notice I have a y here. Now in this notation, see, we've been using function notation, f of x, and then we have something, and then we've been using this, f prime of x, meaning this is the derivative of x. There's nothing wrong with this notation, but when we get into the more complicated derivatives, this gets to be very confusing. So, and I know you're going to say, well, you're about to do this confusing too. Yeah, but it's more explicit. So what we're going to do, we're going to account for what variable we are taking the derivative of. So we're going to use the letter D to mean derivative. So we're going to do the derivative of function y with respect to x. We call this dy dx, the derivative of y with respect to x. And then I just do this derivative, 10x. Okay? And the reason why this is powerful is because I can specify which variable I'm doing the derivative over. So that's going to be helpful if I have a function like this. Okay, so to do this derivative, it's way more complicated than this. Now, we could expand this out 3 times and then distribute the 5, then use the rule that we just used. But that is terrible. We don't want to do that. So we are going to say u is going to be all that extra complicated stuff. You with me? I'm just saying this is too complicated, way too much work. And I'm going to take all this extra stuff and make it this stuff. So y is now going to be 5 times 3x squared, or no, it's going to be 5 times u cubed, because I'm taking u and saying, well, u is this stuff. Okay? And now, when I go to take my derivative, I'm going to say, well, I'm not taking it with respect to x anymore. I'm taking it with respect to y. So dy dx is going to equal dy du times du dx. Well, what does this mean? And probably we won't have time to go over it. What this means is I take the derivative of this with respect to u, and then I take the derivative of u with respect to x, and multiply those. And I will get the derivative of y with respect to x. So, and notice, well, why does this work? Well, although it's not really working like this, you think of concept of fractions, the du's cancel, and giving me dy dx. So, I take the derivative of this part, and I'm going to take the derivative of this part. So du dx, I take this derivative of this u that I did, That's going to be 6x, and then that goes away. I take the derivative of this. I get dy du. Dy du is this. That's going to be 15u squared. And then I multiply those. 15u squared times 6x. And now, while I have this u here, I take this and put it back in. So that's 15 times 3x squared plus 7 times 6x. I can do the 15 times 6. That is, what is that? 90? So 90x times 3x squared plus 7. We could expand that if we wanted. That's dy dx. 270x cubed plus 630x. Do we have time for one more? I think we do have time for one more. One more change. Let's say y is 3 times 4x cubed to the 5th. What should you let u equal?
4x cubed.
4x cubed. Okay, now I'm going to say, well, y equals 3u to the 5th. I find dy du, and I find du dx. I find this derivative. What's that derivative? Yes, 15u to the 4th. And then I find this derivative. What's that derivative?
12x.
Okay, so dy dx equals dy du times du dx. So I take this and multiply it by that. So that's 15u to the 4th times 12x squared. I can put in u. U is 4x cubed to the 4th times 12x squared. I mean, then at this point it's debatable. Do we want to go ahead and expand this? I would say if it's going to be really complicated to do it, then not. And if it's going to be easy, then do it. In this case, it is easy. 4 to the 4th is what? Okay, so we have 256x to the 12th, right? Times 12x squared. And then we do 15 times 256 times 12. We will have something x to the 14th. But then we need to do 15 times 256 times 12. And that gives me dy dx.
It's some really big number.
Big number. Okay, you have a calculator to figure that out. All right, that's we'll stop there.
We're on.